All right, searching and sorting algorithms. Very common problem is you need to search for something, and a lot of times you want to sort something in Excel. So we're going to start talking about at least the basics of these two, and we'll get into some of the more advanced sorting algorithms, but not the super advanced ones. But searching. All right, that's nice. Objectives. So a search algorithm, we've already done search already in your array, and that searches for an item in your array. How long does search occur or take in your array implementation? Oh, then, right. If the data is sorted, is there any way we could speed this up? Probably. Great.
It depends.
You want to think of how, if your data was sorted, what could we do to speed this up?
You can go ahead and jump to the thing.
The thingy?
So like, if it's sorted like through like 1 through 5, you wanted to get to 3, you could just like jump to the middle.
Okay, right. But then you know where that one is. Yeah, jump to the middle.
Well, like,
let's say you had
So I'll break them up into groups.
break them up into groups.
Okay.
Okay.
So like if you have like names that like alphabetized, you could break them up from like A's and B's to A and B. Separately, and then just jump to the A's.
Okay, right. So if you know that all the B's are there, you can just jump to the B section. All right. So that's good. Yeah, good start. Maybe we have numbers and we just have an array of numbers. So if we looked at the middle, let's see what these slides do. They may help you out. Wow, we're going to talk about search where you have a key. Yes, we get it. It's key comparisons, where you compare the key to the item in the list. Sequential search is what we've been talking about. It's iterative solution with a for loop, and we've already talked about it, taking about O of n. Let's go. We should talk about this a little more. The worst case is O of n, because at the very end, you start at the beginning, you have to go to the end. The best case is O of 1, because it happens to be the first element in your array. You're done. But the average, it's probably going to be somewhere in the middle, right? Which ends up being about n plus 1 over 2. The reason for the plus 1 is the first one's O of 1, the second one's 2, et cetera, all the way to n. You know, you add that all up, comes out to about, what they're doing is if you have n searches from 1 to the beginning, the first one's 1, the second one's 2, the 34 all the way up to n, and you did n searches, what would be the average of trying to find each element of the array? It'd be that formula. Go ahead and divide it out, n plus 1 over 2, which is just O of n. On average, it takes about half of n, but that's still O of n algorithm. All right. So binary search. If we go to the middle of the array, what do we know about that? If it's sorted and we go to the middle element, we know
that things to the right of it are greater, and things to the left are lesser.
Right. So we evaluate for greater than or less than on the middle element. First we ask, is it the middle element? No. And then we ask if it's less than. If it's not, what do we know?
Half of your search is done.
Half of the search is done. We just go and search the other upper half. Can we do that again?
Yep.
Yes. So we recurse. Yeah, there you go. Into each half. Here's a good picture. Let's say we're length of 12. They don't tell you what you're looking for, but the middle is 39. If you're looking for the value 75, you know it's bigger than 39. Well, you've just eliminated half of the search space. So now we just need to search the other half. Ooh. So what's the, wow, they're already going to do evaluation. What's the big O of this? People who did not take my class last semester.
Fine.
N plus 1 divided by 2.
Oh, no. That was sequential. How many times are you going to have to call the binary search function?
N divided by 2.
N divided by 2? No. Far less than that. Well, let's think about it this way. Let's go to the board. All right. If you had 1,000,000 elements, and we're just going, let's make this easy. We'll say you have 2 to the 20th elements, which ends up being a little more than 1,000,000. And you do this check, and you find out it's greater than, what's your new search space?
2 to the 10?
No, no. Yeah, 500,000.
500,000, which is 2 to the roughly,
10.
no, that's 1,024. So after
2 to the 17th.
2 to the 19th. After one check, it's 2 to the 19th. And then after 2 checks, what does it become? Like, okay, so we're 2 to the 19th, you know, half of it.
Yeah, 2 to the 18th.
2 to the 8, okay. See where this is going?
Yeah.
So how many checks did you have to do on 1,000,000 elements? 20. So 20 checks for 2 to the 20 elements.
It'd just be 2 to the end.
Hold on. This is for binary. What would it have been for linear search?
1,000,000 checks.
How much?
1,000,000 checks.
500,000 checks. So we'll say 2 to the 19th. Or 2 to the 19th checks for 2 to the 20th elements. Which one's faster? The first one, okay. Each iteration is dividing it by 2. Your search, the amount of work you have to do is halved each time. Which type of algorithm is that? Or which type of, big O is that where you have it every iteration?
Where you have it.
Hmm?
Where you have it, you said?
Yeah, where you have
To
it.
the end, right?
No, to the end is the other thing. To the end would be, what would that be? Oh my goodness. If it was to the end, to the 20th to 2 to the 20th is not 20.
No, yeah.
You did it backwards. It's not 2 to the end, it's,
And to end square.
oh, no, that's the wrong, that was the wrong backwards.
Yeah, no.
Let's see. This is very important to get this clear. When you're having it, maybe we can look at the function here. You're getting close.
I know. You told me not to.
Yeah. I'm trying to think if I can draw this out.
It's fine.
A good way. Am I in the glare? No, good. So, we'll do 1, 2, 4. Oh no, that's not going to help y'all. What would this look like? All right, let's do it this way. Between 2 to the 18th and 2 to the 19th, how many checks would it take? 19. It would take 19 checks for all that in between. You don't go to another check until you double the size. So in other words, this function only grows one step every time you double the size. So, I'm trying to think of a better way of explaining this. It's not to the end, it's, what's the opposite of to the end? Hmm? 1 over n.
So square root.
Square root, that would be square root. Okay, we're getting the right track. Square root is the opposite of n squared,
Yeah.
because
Okay.
square root is actually n to the 1/2.
So this is a log or something?
Yes,
This.
there you go. Because what's the log base 2 of 2 to the 20th?
I'm not good with logs.
Oh, okay. That might be the problem. Log base 2 of 2 to the 20th. You just peel this 20 off. Log base 2 of 2 is 1. It's 20. You can peel the 20 off because it's base 2 at 2 to the. So the answer is 20. Log base 2 of 2 to the 19, 19, et cetera, et cetera. So this algorithm, actually, if I were to map it out, would look something like this. It almost looks like it flat flags. Okay, that's not too good. But it almost looks like it flattens because it barely increases as n becomes linear. You have to increase n a lot in order for this algorithm to jump up anymore. Morning.
So that's n log n.
No. N log n, because n is going to look like this. So n log n is going to look something just a little bit more, because it's growing by that times log n. So it's going to grow a little faster than n, but not too much more. Hmm?
No, I'm talking about the jar test.
Oh, okay.
Sorry, I asked what it means. So.
All right. Put it another way, every iteration cuts the size of the search list in half. It's very important that this is clear how this is coming about, because this is how you're going to do a lot of analysis is based on logarithms, in not only algorithms, but in data structures as well. A lot of good algorithms will have logarithms in their big O. Okay? Everyone got that?
Yeah.
All right, make sure this is clear. The list has 1,024 items, which is 2 to the 10th. At most, 11 iterations are needed to find X. Or I said 10 up there, but 11, sure. Every iteration takes 2 key comparisons, so 22 at most. The maximum comparison is 2 times log base 2 of n plus 2. All right, wow, they don't explain that at all. But the search would require 512 out of the 1,024 elements. Is that all the analysis they say? Wow. All right. Oh, they're going to do a little more on big O notation. So let me stop here.